Hello, everybody. This is the third lesson in Unit 7. So far, we've talked about how to find missing side lengths of right triangles if I know two of the side lengths. And we talked about how to find missing side lengths if I know that two triangles are similar to each other. We're going to put those two lessons together here to talk about a specific case called the 45-45-90 triangle. So buckle your seatbelts, you're in for an exciting ride. Our goal is to be able to look at a 45-45-90 triangle and determine the side lengths. Now, a 45-45-90 triangle, another way of saying that is a right isosceles triangle, okay? So let's kind of use this practice problem here as a starting point, okay? So here we have a right triangle. We know how to solve the missing sides of a right triangle here, but there's something unique about this right triangle, right? Here's my right angle. I know that one side is 5 inches. I know that this side is x, and my goal is to figure out what that is. And so right away we're thinking, oh, it's a Pythagorean theorem. And then we see here that we have a 45-degree angle there, okay? Our goal is to figure out this side. Now, if I'm going to use the Pythagorean theorem, I have a problem. And the problem is that I only know one of the sides. I don't know this other side. Well, again, the 45-45-90 triangle is unique. So the first thing I want to do is I want to find this other angle here. I'm going to call this angle A, okay? So I'm going to say 90 plus 45 plus the measurement of angle A equals 180. So we did that in lesson number 1, okay? Triangle sum theorem. And then combine like terms, and we're going to subtract 135 from both sides, and we end up seeing that A is 45 degrees. So this angle here is 45 degrees. You go, well, what does that matter? I wasn't looking for the angle, I was looking for the side. Well, we got to go back to like elementary school here and talk about, I don't know where you learned this exactly, maybe 7th, 8th grade, I don't remember. But this triangle, it has a right angle, so it's a right triangle. But notice that the two angles are congruent to each other. The other two angles are both 45 degrees. And so that means that the sides that are opposite to those angles, so I'm putting an arrow that's crossing through the triangle from that 45-degree angle, and then I'm going to put an arrow that's going from that 45-degree angle. The two sides that are pointed to from those 45-degree angles are going to end up being congruent to each other. This is a right isosceles triangle. So as a result, we can say that this side is 5 inches. Okay, so we got 5 inches and 5 inches. This is a right isosceles triangle. It's isosceles because these two sides are congruent. The reason these two sides are congruent is because the two angles are congruent. Anytime you see two congruent angles, you get two congruent sides. Now, it doesn't make sense for the hypotenuse to be the one that's congruent because the hypotenuse is the longest one. But now I have enough information to find the third side. And so I would use the Pythagorean theorem here. Remember, the longest side is the hypotenuse, and in this case, the x is the hypotenuse. So we'd say 5 squared plus 5 squared equals x squared. And then we can solve it just like we always do. So we get 25 plus 25 equals x squared, which is 50, right? And then when we go to square root that to get x by itself, I'm going to write this in simplest radical form. So x equals, and I'll factor it, 2 times 5 times 5. Circle our pairs. 1 goes out, 1 disappears. We're left with 5 radical 2. So x is 5 radical 2. So the point is, if you see a right isosceles triangle, you can still find the missing side by doing the Pythagorean theorem, okay? Now that's just a little warm-up, because there's actually a shorter way of doing this, and this way is going to be more beneficial as you progress through math. The Pythagorean theorem is important, don't get me wrong. When you have two sides and you want to find a third side, Pythagorean theorem is the way to go. But if you have a specific case, the 45-45-90 triangle, then there's going to be a better way, a more efficient way, number one, and number two, it's gonna build to future math concepts, like when you get to math 3 and analysis and calculus, okay? So here is, in this diagram, a picture of a 45, 45, 90 triangle, a 45, 45, 90 triangle. We know that this is a right isosceles triangle. Why do we know that? Just like we talked about, there's your right angle, so it's a right triangle. And because the two other angles are the same, this is isosceles. So these two sides, this side and this side, are congruent to each other, the same length, okay? But let's go ahead and, so we'll put the little arc or little congruent marks there to represent that they're the same. Let me have this length be 1. Now I want to find the other two sides. Well, you go, well, that's easy. If this is 1, then that's 1. So we can put that there. And then we can find this third side by doing the Pythagorean theorem, just like we did in the previous problem. So we call that x, and we do 1 squared plus 1 squared equals x squared. And then 1 squared is 1, and 1 squared is 1. So we get 1 plus 1 equals x squared, and then 1 plus 1 is 2. We square root both sides, and 2 is prime, so we just leave it as x equals radical 2. So we just found the third side there, okay? Now, the reason I picked this side length to be 1 is because this is referred to as the parent triangle. Remember, we had earlier on this year, we had parent functions. We had the parent parabola of y equals x squared, and we moved it around a graph. But the parent triangle just means the basic 45, 45, 90 triangle, the one that everything else is built upon, the parent triangle. Now, this is important. You're going to want to write this down. Definitely write the triangle down. Definitely show the work. Definitely have these lengths written in here. But I want you to pay attention to this. All 45, 45, 90 triangles are similar to each other. And in the last lesson, we talked about similarity and how to deal with similarity. So if I have another 45, 45, 90 triangle, then I can find all the missing side lengths by comparing it to the parent triangle, okay? So go ahead and write this down. Pause the video if you have to, but push play and let's see where we end up when you're ready. Okay, and we'd say by AA similarity. We didn't really get into that this year, but that's okay. We just know that the two triangles, or that this triangle is going to be similar to all other triangles that have 45, 45, and 90 as their angles. Okay, so let's go ahead and take a look at an example of this. We'll do 2 examples actually. Our goal is to find the value, the length of the side x and the side y. So let me go ahead and draw this triangle here. You'll notice that I've got my right angle. You'll also notice that I have the 45 degrees, and then I have the 9, the x, and the y. Computer making noises here. All right. Now, the first thing I'm going to do is I'm going to recognize that this is a 45, 45, 90. Why? Well, I have a 90 and a 45, and I can go through all the work again, but I know I'm going to end up with the work of 45 there. So now I can go back to the parent triangle that I just figured out, and I'm going to draw that parent triangle right next to this one. 45, 45, 90. Now, do you remember the side lengths of that 45, 45, 90? Let's go ahead and go back and take a look, okay? What do we notice? In a 45, 45, 90 triangle, the two legs are equal to each other, and they're both 1. The two legs are 1, and the hypotenuse is radical 2. 1, 1, radical 2. It makes sense because 45 and 45 are the same, so the two sides that are across from the 45s are the same as well, 1, 1. And then the hypotenuse is radical 2. So how does that look in my 45, 45, 90 triangle here? Well, we would put a 1 here and a 1 here, and then the hypotenuse is radical 2. The hypotenuse is going to be radical 2 in this case. Okay, so now we have the setup. We have the relationship here. We know that these triangles are similar. So now let's create an equation that puts it all together. And this is what we talked about in the last lesson. These triangles are similar. That means the sides are proportional. So I can set up a ratio. I'm going to pick a side here. I'm going to say x. Well, what does x go with? X corresponds with 1. They're both the sides that are between the 90 degree and the 45 degree. They're in the same position here. okay? And that's going to be equal to, pick another side in this triangle to put on top. That's going to be equal to 9, and 9 goes over 1, okay? Now, the other one would be then y over radical 2. We can write all of that out, but if I'm just looking for one side, I'm just going to focus on 1 for right now. So it'd be x over 1 equals 9 over 1. Now, for some of you, you might be going, well, I already know what x is. That's simple, right? X is 9. And you're correct, because it's a 45, 45, 90. That's 9, and that's 9. But let's do the work just to make sure. We're going to, because we have an equal sign between two ratios, we're going to cross multiply here. So we end up with x times 1 is x, and then cross multiply here, 9 times 1 is 9. And so now I know the value of x. I know that length, okay? Now let's focus on finding y. So I'm going to set that up. It's going to be y. Well, y corresponds with radical 2, and that's equal to another ratio. So I could use the x over 1, or I could use the 9 over 1. Because I already have a variable here, I don't want another variable. So I'm going to go with 9 over 1. So y over rad 2 equals 9 over 1. And you can see it here. Y over rad 2 equals 9 over 1. Okay? Then we're going to cross multiply. So y times 1 is y. And then 9 times rad 2 is 9 radical 2. And that's my answer. We're done. Okay? So you can see if you can set up the ratios, there's no Pythagorean theorem to do. It's actually pretty quick. Now we can do the Pythagorean theorem. We could say 9 squared plus 9 squared, because that's also 9, is equal to y squared. We end up with 81 plus 81 equals y squared. We get 162 equals y squared. Then we square root both sides, right? And we've got a prison break now. 162 is 2 times 3 times 3 times 3 times 3. Okay, circle your pairs. We've got a 3 going out, another 3 going out, and then the radical 2. So we're left with y equals 9 radical 2. So we can see that the answer is the same, but you can see the amount of work for this was far more than just setting up the ratio and cross multiplying. Okay. Well, how do we set up again the special right triangle, the 45, 45, 90? The 1 and the 1 are the legs, and the rad 2 is the hypotenuse, and then we just set up proportions because these triangles are similar. All right, let's go ahead and take a look at another example, and then I'll have 2 practice problems for you to do. Okay, so for B, we have a right triangle that's kind of sitting a little funky here, right? We've got the right angle there. We've got the 45-degree angle there. We've got X, we've got Y, and we've got 22, okay? Now I'm going to draw right next to it, I'm going to draw my parent triangle. Now it's not to scale because I can't draw that small. But here's my parent triangle. There's my 45, there's my 45. In a 45, 45, 90, what are the side lengths? It's 1, 1, and radical 2. So where does the radical 2 go? It goes on the hypotenuse, and then the 2 legs are the 1s. From here, we'll set up ratios. So we'll pick a side here. I like starting with a variable. I just always like starting with a variable. X, what does X correspond with in the other triangle? X corresponds with the 1. And that will be equal to, now I want another fraction, another ratio, that doesn't have variables in it. So I don't want the y there, okay, because then I can't solve it. I got 22 here, so x over 1 equals 22 over rad 2. Now notice, just to double check yourself, you want to make sure that everything in one triangle is together. So you want to make sure that if x is on top, that the 22 and the y is also on top. If 1 is on the bottom, then you want to make sure the 1 and the rad 2 are also on the bottom when you go to solve those, okay? So the top is one triangle, the bottom is the other triangle. From here, we cross multiply, okay? So we end up with rad 2, if you want, times x equals 22 times 1, which is just 22. And then we'll go ahead and divide by radical 2 to get x by itself. So we get an answer of x equals 22 over radical 2. Now there's a problem with that. Remember the problem. You can't have a radical in the denominator. That's not considered okay. So how do we get rid of that? We multiply it by rad 2 over rad 2. And so remember, we end up with x equals 22 rad 2 on top, and then the rad 2 times the rad 2 can be written as radical 4, but that just simplifies to 2, okay? We've done all this when we were talking about radicals in previous units. And then we can reduce the top and the bottom both by 2. Remember, we divide the non-radicals and then we divide the radicals. So we're going to divide the 2 into the 22 and the 2. So we end up with on top 11 radical 2 and on the bottom, which is 1. But we can just say that x is 11 radical 2. So that is my answer for x, okay? You go, boy, that was a lot of work. It wasn't that bad, especially once you get used to it. You just got to make sure that the fractions are set up right. All right, let's go ahead and set up for y. We'd say y over, what does y go with? Y goes with the 1 equals the 22 over radical 2. Now you can see that these actually are set up the same way. The only difference is the variable here. So we know that our answer is going to end up being the same as what we got for x. Y equals 11 radical 2, and we're done. If you wanted to see it in a different way, you could have said y over 1 equals, now we know what x is. Remember, x was 11 rad 2, so we can write that down here. This is 11 rad 2, so we could say 11 rad 2 over 1. And then we could cross multiply that if we wanted to, and that one's easier to do. So we end up with y equals 11 radical 2. Okay, so a couple different ways of doing it. You could also recognize that, look, these two sides are the same, therefore these two sides will be the same. And since I already found x, y is going to be the same thing. Okay. All right, so there's that. Make sure you have those written down as examples before you go on. But let's go ahead and go on and do some practice problems here. Okay, I got 2 problems for you that are just like the ones we just did. Okay, so for this one, I call it number 3. I don't know if it's actually number 3 or not, but that's okay. We'll draw the triangle that we're talking about here. And we know that this side is 22, and we got a 45-degree angle and another 45-degree angle. And because it's 45, 45, 90, we're going to look at our parent triangle of our 45, 45, 90. Remember the side lengths, the 1 and the 1 are the 2 legs, and the radical 2 is the hypotenuse. Okay, I'll call this, I don't know, R, and this one Q, just to be different. So we'd set up a ratio. We'd say R over 1 equals 22 over 1, and then we cross multiply. So 1 times R is R, 22 times 1 is 22, so we have R. We knew that anyways without doing any work because these two are the same, these two will be the same. R is 22. Then the other one for Q, we're going to say Q over radical 2 equals 22 over 1. Then we cross multiply those. We end up with Q equals 22 radical 2. And that is our answer there. Okay. All right, so that's how we do number 3. Number 3 was an easier problem, to be honest, right? Let's go ahead and take a look at number 4. Hopefully you've already done it and you're ready to go over it. But let's see what we get here for number 4. We have our 45, 45, 90 triangle. And that's 45 there, and that's 36. Because that's 45, we know that this guy's going to be 45 over here, but we're going to draw our parent triangle. And we've got our 45, our 45. Well, which one's the hypotenuse here? This bottom one's the hypotenuse, so that's radical 2. And then the legs are 1 and 1. I do want to emphasize, though, that these lengths only work in a 45, 45, 90 triangle. You can't just put 1, 1, rad 2 on any right triangle. It only works for the 45, 45, 90 kind, okay? The next lesson, we're going to be talking about the 30, 60, 90 triangle, and those lengths will be different. So you want to make sure that these go with the 45, 45, 90, okay? So I'll call this side A and this side B. To set up for A, we'd say A goes with 1. Of corresponds with 1, and that's going to be equal to, we want to pick another one from this triangle that I know, that'll be 36 over radical 2. And then we'll go ahead and cross multiply here. If you're seeing a quick shortcut here, that's okay. We get rad 2 times a, and then on the other side, we end up with 36 times 1, which is 36. And then we divide by radical 2, and we end up with a equals 36 over radical 2. Again, that answer is not okay because the radical's in the denominator. So we're going to multiply that by radical 2 over radical 2. And we end up with a equals 36 radical 2 all over 2, right? Rad 2 times rad 2 is 2. And then we can reduce the 36 and the 2 both by 2. And we would end up with a equals 18 radical 2. Okay, 18 radical 2. Now for b, b's easy because a and b are the same. 1 and 1, these are the same. So that means b is also going to be 18 radical 2. Okay, so that is how you solve for missing sides of a 45, 45, 90 triangle, or another way of saying that, a right isosceles triangle. Okay, if you have any questions, please comment below. Otherwise, I'll see you around.